talk about normalization. And normalization is a process by which we evaluate the tables that we created during our ER model. And we we ensure that any data redundancies are removed, and that helps us to ensure that our database is free of data anomalies and has data integrity. Everywhere I've been in industry, we've taken a look at the normal forms of our data and made sure we were in third normal form. So I think it's something you'll find useful in the future. Well, our objective is to learn what the process is, what the normal forms really mean, what each condition of the database is when it's in first normal form, second normal form, and third normal form. That's usually the level we need to go to for industry type problems. There are some other normal forms that are sort of interesting, and so we'll talk about those too. We talk about the process of, and that's what normalization really is. It's this process that we use to first ensure all of our tables are in first normal form, then that all of our tables are in second normal form, and then finally that all of our tables are in third normal form. Then there are some times when performance is an issue, and I would say only after proven to be a problem, we can do denormalization. And what denormalization does is it's possible to make things somewhat more efficient in some situations, but it's unlikely that you'll really need to do that, in my opinion. So the first thing we need to talk about is what are functional dependencies. And because functional dependencies form the basis for all of the normalization decision. This is sort of like thinking with functional dependencies about your data. So if you remember functional dependency, it's the idea that one attribute functionally determines another attribute. And so that's what we'll be talking about to start with tonight. Then we'll look at the data anomalies. Finally, in the normalization processes, we'll spend most of our time. And then last, I'll spend a minute or two on denormalization. Well, the normalization process is to ensure that our data are all dependent upon the key. Right? That's our primary mission. The mantra for normalization is every non-key attribute must be fully functionally dependent upon the key, the entire key, and nothing but the key. And so what we're trying to do is make sure that all of our tables refer to one single topic, like customers or student or invoice line. And all those, over all of our attributes, we've never stored one fact more than once. And so this is our goal. And if we achieve this, we are ensured that we have no anomalies in our design. And the good news is when we start from an ER model, we are usually in third normal form at that point. And that's just because of the way the techniques we have for developing ER models sort of leads us to the correct solution in terms of normalization. Well, so it's a process of finding attributes that are not fully functionally dependent upon the key, the entire key, and nothing but the key. And then removing those attributes from the table where we find this discrepancy or this violation of functional dependency rules, right? The only functional dependencies we want in our system is where each non-key attribute is dependent only upon the entire key. And so that is our goal. And by doing this, we will minimize all of our data redundancies, and then also remove all anomalies. And so we're going to go through a process of first normal form, where we evaluate every attribute in every table to ensure that it is dependent upon the key. And then we go through any tables that have composite keys and evaluate them for second normal form to be sure that all non-key attributes are dependent upon the whole key and not just part of the key. And then finally we go through every attribute of every table to determine if that attribute is functionally determined by another non-key attribute. That is, an attribute that's not part of the key. And if it is, we decompose by taking those two attributes that are offending in this point, where the non-key attribute functionally determines some other non-key attribute, and we then decompose that, move those attributes to another table. And so that's our process. And normalization, I think you could be expected to be given a set of relations and asked to say what normal form of these relations in and why. I think that'd be a valid question if you were going to apply for some sort of database related position. Well, redundancy makes these anomalies. And so if we imagine that instead of storing each fact once, we store a fact multiple times, then that means that we're going to have to do some more work if something changes on that attribute. So an update anomaly is that it is when our database has this characteristic where we have stored data redundantly, where we've stored something like your major, and instead of storing your major as a fact that describes the student, we could store major as an attribute of section, where we say for every course you've taken, what your major is. Now, there's no reason to do that in a normal requirements for a university system, but we could. If we did, and you changed your major, which we know some number of students do every year, and when you change your major, we'd have to go find all the places where we've stored it and then change it there too. And if we didn't manage to do that, if we didn't manage to find every one of the places where we've stored it and fix it, or change it to the new one, then we would have an update anomaly. And our database would not be consistent, because we would have one major in one place and another major that isn't correct in another place. And we need to avoid that situation, and that's why we have normalization process, to be sure that we store each fact only one time. Well, suppose we did this idea and we have this thought that we're going to store the major with every course you take. And, on that section table, right? So we have student ID. Let's go with section ID as a key. Then we have student ID as a foreign key, and course ID as a foreign key. And now we put major in there as a foreign key, right? So we've stored it in that relation, all right? And then suppose that we've made it not null, meaning that you got to have a value. We couldn't insert a new instance of section for a student that hadn't declared a major yet, right? That would be incorrect. It would be incorrect to say this student cannot take a class because they don't have a major. Now, we could make up a fake major like missing and put those values in there, or put a none or some value in there that we could then put in the major table. But you see, that is just like causing data integrity problems in your system just to work around an insertion anomaly that was put in there by a bad design. And so avoiding that idea of redundancy and trying to make sure that every fact, every attribute of every table is associated only with that thing that is data are being stored about is really important. Well, deletion anomaly is the idea that once we've used some value, then we have to be careful when we come along and delete it. Suppose we had a major of information systems, IS, just call it. And in that major, at one point we come along and we decide we're no longer going to have a major of IS. Right? So if we decide to delete that major of IS, what should happen? Should all the students who were IS majors before we decided to drop that major, should all of their records be deleted because we deleted that major? That would make sense, wouldn't it? Because each one of those students' records would have pointed to an instance of another entity that doesn't exist, right? There'd be no row in the major table for IS anymore. Maybe it's ACIS or something, but it's not there. And so now if you delete that, what happens? And so the idea that there would be something out there pointing to that or referencing that thing that was deleted that also wasn't deleted is the idea of a deletion anomaly. Well, I know we've talked about the idea of functional dependency before, but I think I want to do this is a little more important in terms of the reason you learned about functional dependency before is so that you can do some of this normalization stuff that makes more sense. So functional dependency, you'll recall, is a relationship between attributes. We say A functionally determines B. Right here we say A functionally determines B. B is functionally dependent on A, or A determines B. So what that means is for every value of A, there is only one value of B that is appropriate and associated with it. So if you know the value of A, you also know the value of B. It will always be the same. And so what we're trying to do is set up this situation where, well, we're not trying to do it, we are doing it, where the primary key functionally determines all other non-key attributes. That's what we do. And that's what ER modeling helps you to do. We make sure that this is true for every attribute. And here is our mantra. Each non-prime attribute of a relation must be fully functionally dependent upon the key, the entire key, and nothing but the key. So here's a functional dependency example. Here's 3 different orders. And on these orders, the same 3 items are presented. Right? I have a fishing rod, a fishing reel and fishing lures, a fishing rod, a fishing reel, and fishing lures. I actually don't do that much fishing anymore, but let's suppose. And if I ask you, what is the quantity purchased? What could be your answer? I guess you could give me any of these quantities, 2, 1, or 5, 4, 2, or 10, right? But I'm going to say this time, all right, well, the quantity is for item 20, right? And now you have to ask, can you tell me what quantity I want? Not really. You can just tell me if I want this 20, or this 20, right? And now suppose I say that I want See what you see? You don't know. You don't have enough information to know what the quantity is. Right? So quantity is not functionally determined just by item number. Right? It's not determined just by item number. Because I just told you what item number I wanted, but you couldn't tell me what quantity was the correct one. But now if I tell you the order number I want is 9002, now you have enough information. You know both the order number and the quantity number, so you can tell me that the proper quantity is 2. And so this is what functional dependency means. It means, what do you need to know the value of the attribute that you are interested in? Excuse me, had to sneeze there. So, that's the idea of functional dependency. What do you need to know the value of the attribute? In this case, the attribute quantity is functionally determined by both the order number and the item number. Well, the primary key is the most important thing we have going in the relational model, because we know you use your primary keys also as foreign keys. And so from a functional dependency perspective, it's the minimum set of attributes that functionally determine all other attributes. And here would be our typical situation where we would want to have a PID. A physician ID functionally determines a physician name and physician telephone. That where the physician ID is the primary key. If there is more than one primary key, we have to select one. And I guess it's possible that you could say that the telephone also is a valid key. They're both candidate to be key, perhaps. The condition that it never changes over time, for me, would sort of make telephone not a valid key from my perspective. I'd rather not use it if possible, but I see where being able to look things up and use it as sort of a surrogate key would be fine. But to me, the key here would always be physician ID. But if it's possible, there are two things that could be key. We have to pick one as our primary key, just as we have already done in the ER model. So I think as you're thinking about what you already know, your ER model already has primary keys. And if it doesn't, your model's incomplete and needs fixed. Well, so our goal in normalization is to make sure all of our tables are in third normal form. And what that means is every non-key attribute must be fully functionally dependent upon the key, the whole key, and nothing but the key. And we work on one relation at a time, and we do each attribute. We look at every attribute to make sure that there are none of these functional dependencies that we don't want in our system. And so the first thing we do is identify all the functional dependencies in the table, and then progressively work through those dependencies to get down to where only the ones we want are represented, and we eliminate the ones we don't want by creating new tables to place them into. Well, there's two types of functional dependencies that we have to eliminate. The first is a second normal form violation, and that is a partial dependency. And that means that a non-key attribute is functionally dependent on only a part of a composite key. And that's just a problem. Now, an example of that would be, suppose we stored part description as part of invoice line. And in our invoice line, we have the primary key of invoice number and part number combined to be the key of invoice of this version of invoice line. And now we add an attribute of product description. Well, product description is not determined by the entire key. It's determined by only the product number. So if you know the product number, then you know the product description. So product description is determined by a part of the key of invoice line. And that is a second normal form violation. What we would do in this case is we would just say, oops, description, which I'm sure also is in product or belongs in product. And that would solve that problem. Anyhow, transitive dependencies is when a non-key attribute is dependent upon some other non-key attribute. And this is a bad situation because remember our goal is to have every attribute fully functionally dependent upon the key, the entire key, and nothing but the key. Well, our an unnormalized relation, and we shouldn't have any of these coming out of our process of ER modeling, means it has no primary key, and it has multi-valued attributes. Well, we've learned before that the relational model doesn't allow multi-valued attributes. And we've learned that whenever we have a multi-valued attribute, what we do is we make a new entity for that multi-valued attribute, and then we take the primary key of the previous entity which had the multi-valued attribute or a repeating group of attributes, and we then make that a foreign key in this new table. And so we already have learned in our ER techniques, entity relationship modeling techniques, to eliminate this anomaly or to not have unnormalized relations in those models. So here's the universal relation R. And in it, we have attributes of student ID, courses the student has taken, majors the student have had. That is an unnormalized data set. Right? And these are repeating groups. Even if we said that student ID was the key, courses is a repeating group of things, and as we've discussed earlier, majors are changed. Right? So that's not appropriate. So here are some values. S1 is a value for student ID. And then here's the repeating group of values for classes. And then here's the repeating group of classes where it looks like the major name. Well, I guess both majors are CS and MIS, Management Information Systems. So this is a relation that is unnormalized. It is not in first normal form. And so you shouldn't have any of these coming out of your ER modeling techniques if you've followed our rules. Well, so what do you do to convert to first normal form if you haven't already done this in the process of developing your ER model? You remove your repeating groups. And so what we do is we have to come up with a way to make sure that we don't have these repeating groups. And so the process for converting to third normal form has a series of steps. First is we make a tabular, put our data as though it were a table, and there is so that the repeating group has a single value. So it's sort of what we're getting is where before we had the classes DBMS and we had the DBMS. I can't even see that when I select it. we had DBMS, a DBMS class, and a programming class, and another class. Instead of having our data that way, what we want to have is we want to have student ID DBMS, student ID Java, student ID networking, whatever the other class is. And so that's what we do. We take those repeating groups and we put them into a new table, and then we come back and make a foreign key. I mean, we still are going to need that student table, so we're going to then make a foreign key to these new table with repeating groups. And so identify the primary key. We should already have this, as I said, coming out of our ER model. If there are candidate keys, which is usually rare, there shouldn't be too many situations where you have a lot of, or you have any true valid candidate keys. It's possible you might identify a new key, but I'm hoping well, you should never come from an ER model without without a key. That should be impossible. So I like dependency diagrams, and of course you've seen them in the book, and basically you just draw an arrow from the determinants to the dependent, and that way you get to get a good look graphically. And I know I have like a tendency or something to the graphical things, like the ER diagram and this type of functional dependency diagrams. I just think diagrams carry a lot more information sometimes than textual representations. But the truth is we have to be able to deal with any type of representation. And once we understand the key ideas, which I think you already no pun intended, the primary key, foreign key, and those concepts, once you understand those, and I think by now you should, you should be able to deal with the issues conceptually in your mind without either relational model, a picture of columns and tables and things like that, or the ER diagram. So conceptually, that's where you need to get to. But I think these are nice little diagrams, these dependency diagrams. And so what we have here is where our key is these two attributes, where the project num and the employee num, that's our key. And so we're saying that it should determine every attribute. That's a functional dependency we assert when we say it is the key. And then it also inserts the project name. And so that idea that's the only functional dependency that we want to exist in this system. But this relation contains dependencies that are not appropriate. First off, let's say this relation is in first normal form. It's in first normal form because it has a key and it has no repeating groups. Right? Therefore, we are in first normal form. However, we're not in second normal form, because second normal form is the removal of partial dependencies. And this is the idea of a partial dependency. Here we say the project number functionally determines the project name. Now we know that the project number is only a part of the key because the key is project number plus employee number. So the project name is being determined only by a part of the key, the project number. All I need to know the project name is know the project number. I don't need to know the employee number to know the project name. I only need to know the project number. Similarly, to know the employee name, all I need to know is the employee number. The employee's name doesn't change depending on what project they're on. So the entire key of project number and employee number is not needed to know the appropriate value of employee number or employee name. There is a partial dependency of a part of the key, employee number, determining the employee name attribute. And that's also true for the job class, right? Whatever the employee's job class is, engineer, clerk, management, it depends on what their employee number is, not on what project number and employee number they're working on. Well, so another dependency here, and these partial dependencies are what we call second normal form violations. And finally here we also have a third normal form violation, a transitive dependency, where the only thing you need to know the charge hour is to know the job class. So if you know the job class of the employee, you also know the job hour, the charge per hour for that job class. So even though this relation is in first normal form, it is not in second normal form. So to go to second normal form, our goal is to eliminate those partial dependencies that we just saw on that prior page, where the project number drives, or to know the project name, all you need to know is the project number. And to know the employee job class, all you need to know is the employee number, not the employee number and the project number. Right? So we've seen what these partial dependencies are, and so what do we do about it? Well, so an easy way to work through this is to just take each key component and write it on a separate line, and then write the composite on a third line. Then look at each one of the components to become a new relation if it determines any non-key attribute. All right, so that's simple enough. If we have our previous slide so we should have a line for project and a line for employee, and then a line for project and employee. So that's project num on one line, employee num on the next line, project num plus employee num on the third line. So now we're ready to write down the attributes that go on there. And if you remember from our previous slide, what those attributes are going to be is on project num, next to project num, we're going to say project num functionally determines project name. And then we're going to say employee number functionally determines employee name, employee job class. And then the composite relation is going to the third line of our page, where we have the composite key of project number and employee num, is going to determine only hours. The hours worked for this employee on this project. And you can see that makes sense, right? It makes sense to say that to know how many hours are worked on this project, we need to make sure that hours are associated with the project. And to know for employee, we need to know how many of these hours were for employees. So you need to know both project number and employee number to know how many hours were worked by the employee on the project. See, that's the fact we're recording there. The number of hours worked by the employee on the project. Well, so then you go through and for each one of those dependent attributes, where you do have dependent attributes on those keys, you make a new entity. Right? We take a new relation with the component as the key, including the attributes it determines. Then we take that key, right? That key component stays in the original relation, and it becomes a foreign key to this new relation. Any dependent attributes that were dependent on that part of the key are moved from the original relation and are now only in the new relation. So here's our new set of relations that we have after we have converted to second normal form. So we have the project number determines the project name, and we have a new relation, project num, project name. We have the employee number determines the employee name and the job class. And now we still have an issue with this, but it's not a second normal form issue. This relation, employee, is now in second normal form, and it's in second normal form because it has no partial dependencies. Note that you can only have a partial dependency whenever there is a composite key. Now, some brilliant students say, well, I will never have a partial dependency because I will just never define a composite key. All you do when you do that is move any potential dependency problems you have, you just change them from partial dependencies to transitive dependencies. So that's not a good strategy, but it will get you into second normal form. If you never have a relation that has a composite key, then you will be in second normal form by definition. Well, finally, we come down here to our assignment relation, and we see that to know the project number and employee number, you need to know those things to know how many hours the employee was working on that project. And so at this point, we've gone from one relation to one relation that was in first normal form to three relations that now are in second normal form. Well, a database is in second normal form if all the relations are previously in first normal form and we've eliminated all partial dependencies. At which point all relations in the database are second normal form. Then we can say our database is in second normal form. And that's where you can see that even if you have one table that's out of whack, your entire database is considered unnormalized or normalized only to a certain normal form. If you have just one table that is in second normal form but not third normal form, then your entire database is in that normal form. Well, so we've removed our partial dependencies, and our next thing to do is remove any transitive dependencies. And that, you'll recall, a transitive dependency is when a non-key attribute functionally determines another non-key attribute. And that's a violation of our goal of the entire key. Or remember, our goal is the key, the entire key, and nothing but the key. And transitive dependencies are violations of nothing but the key. Right? You can't be dependent on any other attribute than the key attribute, and that's a transitive dependency. And so we put a table into third normal form if it is previously in second normal form and it contains no transitive dependencies, meaning that no non-key attribute determines any other non-key attribute. Well, to eliminate transitive dependencies, you start out, and for every transitive dependency you find, write its determinant as the primary key for a new relation. Notice the same thing we do, right, in first normal form whenever we had a problem with our our relation having repeating groups, what do we do? Create a new entity or a new table for those repeating groups. What did we do when we had partial dependencies? Well, we took that part of the key and we made a new table for that part of the key and the attributes it determined. Well, whenever we have transitive dependency, we're going to do a similar thing. We're going to take those primary keys. We're going to consider those attributes that determine other attributes as primary keys for new relations. So then once we have identified the potential other determinants in our model, right? Now we had assigned those other attributes that they determine to those new relations, and so we have the attribute that was the determinant as the key, and the dependent attribute as an attribute in that new relation that is determined by that key. And so that's what we do. So now we have a new relation with a primary key and attribute, but we also leave that determinant, that new primary key value, as a foreign key in the previous relation, and that remains or maintains the link between the prior instances and that dependent data, so that we still have, our model is still correct. It's just that now the data are in a different table, and so we've created a new table in a relationship to that table that replace the original table. Well, so our transitive dependency, you'll recall, was where the only thing you needed to know the charge per hour for a particular job class was the job class, right? It's not dependent upon the key of employee, right? The charge hour is not determined by the employee num, it's determined by the job class. So what we do is we decompose so that the job class, right? We have a new table job with job class as the key and charge hour as the only attribute. But we maintain in employee the job class attribute so that we know what job class an employee is in. Job class in employee is a foreign key, FK, into job class. And so that's what we do with our to get into the third normal form. If there are any transitive dependencies, we remove them by creating this new table job. And so from our original relation, we've now ended up with 4 relations that are the proper representation of the data for our system. Back in the day, the way we learned to do this process of normalization was we just put all the attributes for the entire system. This is the way they taught it. All the attributes for the entire system in the universal relation R. And then you just kept applying these rules and applying these rules and applying these rules until you got down to the set of relations that were appropriate for the system. And that process was a lot more cumbersome than the current process, where you start from an already nearly perfect model that emerges from the ER modeling process, and apply these rules to that model, and it makes things much simpler and much less work to do. Well, I think you see here that these are just sort of rules that are functional dependency driven. Now, as long as your functional dependencies are well rooted in your business rules, you're okay, right? You should still have a good design. But what we're doing is we're trying to get the perfect answer, the good design first, and then checking that good design, that thing that comes from the ER model, to make sure it has the characteristics that we really want, or that we need. You know, normalization is more of a technical correctness design kind of thing than a proper requirements problem kind of thing. And so it's undeniable to me that the most important part is getting the problem right, and then the solution to that problem right. If you have the wrong design, normalization can't save you, right? If your design is bad, following these rules, eliminating dependencies, isn't going to save you. If your design is wrong, you have the wrong dependencies. So making sure that there's no partial or transitive dependencies doesn't help you because you haven't identified the correct dependencies. That's the most important part. This is an important part because we don't or can't have data anomalies in our models. And this process is how we remove our data redundancies that cause those anomalies. Well, we must have atomic attributes, right? I know phone number can be okay, I guess, even though we know it consists of a few parts. If you ever need those parts, though, they would have to be subdivided. That's what the atomic idea is, right? You don't want to have area code, exchange, and number not be attributes if you're going to ever need those data. Well, you want to make sure that your primary keys are as natural and simple as possible. That's a really critical thing. And I think on derived attributes, I don't think you should have any derived attributes. I think I said this back in your modeling. Any derived attributes that don't come from the attributes of an instance should really be considered, right? I would only make those attributes under performance characteristics also, right? I'm not going to try to derive something live that's going to require a table scan, usually, because then you're building in a situation where you're always waiting. Well, so here's a third normal form database for employee. If you take a look at these attributes, employee last name, first name, initial, hire date, and job code, those are all things that are fully functionally determined by the employee number. Similarly, here we have project. Project determines the project name and the employee number. That's what this project is telling us, is what is the name of the project and who is the project manager. Here we have another table, job, where we can know the job description and the hours to charge for any particular job. And we can see that database designer is the best of all jobs. And not only is it the best of all jobs because it pays the most, it's also the most interesting. And it's not nearly as much more interesting than programming, or not nearly as tedious as programming. But I like programming too. Anyhow, so then our last project is assignment. And you see here we have the derived attribute of how much the how much we're going to charge for this project. Now, I think this is a really nice example. It shows our how our database turns out, and it's the result of normalization that we never are storing any fact twice. Now, you might ask, well, how come I have to store the charge hour? Right? That sort of seems like I'm storing that twice. And the reason you have to store it so that you can use it to derive the assigned charge is that, over time our charge hours could change. Right? And at this date, this was the appropriate charge hour. So we should or must record it, because if we don't record it here and use it to derive assigned charge, then we're going to have to come back to charge hour and employee. And if we make changes to any of our billing rates for our job descriptions, then we are going to have an invalid assigned charge. So we do have to. That is not a redundant fact. This is the charge assigned at this date and time for this employee on this project. This fact in job is this is what we currently pay people working in this job description. Well, there's some additional normal forms, and the first one beyond third normal form is a Boyce Codd normal form. Most people aren't too interested in this kind of thing from a industry perspective because it's really rare. What it means is that some non-key attribute determines an attribute that's part of the key. It's very rare. I mean, if you're using a ER modeling approach, the idea that you would create something like this, a violation of this type, is very rare. It can only happen when there is more than one candidate key, and it also can only happen whenever there is a composite key. So if you don't have, and we said both of these situations are relatively rare. It's rare that you're going to have two valid candidate keys. To me, that's highly unlikely. And then it's also, it's not, we do have many relations that have composite keys, but the idea that you would make a functional dependency that is where a non-key attribute determines a part of the key is, I think, unlikely. Well, Boyce Codd normal form, it's a situation where you can be in third normal form only. You usually are in third normal form. You have to be before your Boyce Codd normal form. But you can only have a Boyce Codd normal form violation if you have a non-key attribute determines an attribute that's part of the key. So you must have a composite key, and this is, I think, a rare situation to have this problem. Well, so I got a couple examples here. So here we say that C determines B, right? Our key is A and B, and it should determine C and D. But if you have the situation of C determines B, this is your Boyce Codd normal form violation. Well, so what you do when you have this situation is you take this offending attribute here, this C determines B, and you do what we usually do. We break it out into its own entity. And so now what we say is that A and C determine D. right? We had our key wrong. We had A and B determine C and D. But then we realized we had a functional dependency C determines D. C determines B. And when we saw that, we know that we can know the value of B if we know the value of C. Therefore, we can replace it in the key of this relation and now have relations that are both third normal form and a Boyce-Codd normal form. And you remember, this is in third normal form. Why? Because no non-key attribute determines any other non-key attribute. No transitive dependencies. And so that's why that relation is there. But this functional dependency is not something we'd want to have in our system. So in the unlikely event you have it, it'd make sense to remove it in my mind. Well, so here's a little more of a better example, sort of some real life, where the class code determines the staff ID. And what we're looking for is to say this student took this class and got this grade. Now, it's also a detail that this class was taught by this person, but the real fact, the fact you're trying to record, enroll grade, is dependent on more, to my mind, on the student ID and the class code. And sure enough, if you decompose this into Boyce-Codd normal form, you get a model, I think, that makes more sense, where the class code determines who is the professor, and the student ID and the class code determine the grade. Well, fourth normal form is when you have third normal form and no multi-valued sets of, or no multiple sets of multi-valued dependencies. What happens here is when you're trying to store two different facts in one instance, and the problem is that you can't tell which fact the instance is for. And so basically what you do is you create two tables instead of one table for each multi-valued fact. Now, you should never have this problem coming out of an ER diagram either, because your models should have produced different tables for each multi-valued attribute. Well, so here's the idea. So we have this table, volunteer 2, and in this table we have the fact that the employee works for an org code, and we have the fact that the employee is assigned to a particular assignment. So these are two different facts. And so sort of the more accurate thing would be to, instead of trying to store them both in the same entity, is to give them different entities. And so this is the problem you have, is when you, like in volunteer 3 here, right? The problem you have is the attributes on this instance are not related to each other. They record two different facts. They record that 1023 works for RC, and 1023 is assigned to number 3. But the org and the assignment aren't related to each other. So what you really want to do is you want to have two different tables so that you store each of those facts, like what organizations people work with, and then what service they're on, as two different things. And that is the idea of fourth normal form. But again, you shouldn't have fourth normal form problem whenever you are starting from an ER model, because it's unlikely that you would combine these things together. Here we have what an employee has done, and here we have a list of organizations. Those things would have been, or a list of organizations, and then also a list of assignments. All right. Well, so here's our table sort of presented as an ER model with attributes. I don't think you should have any issues with these models. It's a relatively simple model. Hopefully by now you can take a look at this model and be able to say that there are no partial dependencies. There are no transitive dependencies. Therefore, our model is normalized. I think everywhere I've been, we've done normalization. I think because maybe because we're old and we all started doing normalization before we had ER kind of thing. But it's well worth taking the time to look at. And like I said, once you have started from an ER model, the likelihood that you have a decent model is pretty good. So the work you have to do to normalize is not dramatic. But it's well worth running it as a check process, even if it's not the design method it once was, because now the true solution to the problem is formed with the ER model. Denormalization. Denormalization means storing some things redundantly to make it easier to access them or faster to access them. One of the things that I think you might end up doing is calculating some derived attributes that run across multiple tables. Of course, it can't be too dynamic of a process, but that is something where you then store that calculated value, and that helps increase your processing speed and requirements, and it is denormalized. I would say the only reason you should denormalize is whenever you've already demonstrated that your model is insufficient from a performance perspective. Well, the thing is that whenever you denormalize, you have to handle it in code. Whatever the system would have done for you automatically, now you have to make sure that you write extra code to maintain the data redundancies that you've incorporated when you denormalized. And so it's just, as long as you know exactly what you've done, then you can write the code to make sure that you keep it, your data integrity. But it just adds more work to your world, and it builds in the potential for anomalies that you then have to control with your data checking, cleaning, and that kind of processes. Well, I think here's a nice little list of things you can use for helping improve your data models. Sort of gets you down into thinking about the design perspective. And for me, I'm still more interested in that you get the right problem. Because if you don't have the problem expressed correctly, it's very difficult to get to the right answer. Nearly impossible. Well, we do need normalization. It helps us to make sure we're free of data anomalies. I think you see the process now. Basically the process is we identify offending attributes and we remove those offending attributes to different tables and create a foreign key to those tables to maintain our relationship. And it's I think, a really important thing, and I think that wherever you go, you'll have to understand it, and there'll be people there that care about it. Well, second normal form, third normal form. Second normal form is partial dependencies. Third normal form is transitive dependencies. Right? It's part of design, but I guess if there's one last thought to think, it's that normalization isn't going to give you the correct design. Right? It's not going to make sure that your design solves the problem. What it's going to do is make sure the design that you've created to solve the problem is free of any any data anomalies that are going to cause problems in your system. So you should do it. And with that, I will end.